This lesson is about the inverse square law. Remember that the inverse square law is commonly used in radiography and in radiation physics to describe how the X-ray beam changes when the distance changes. The inverse square law is actually described by this formula. This is the most common representation of the inverse square law formula, but I personally don't find it especially helpful. It's not easy, it's not practical for use. And so this second formula I personally recommend when using the inverse square law to solve particular equations. I2, which is the intensity, is equal to the first intensity multiplied by a ratio of the squared distances. And for this more practical formula, I2 is equal to I1 multiplied by D1 squared over D2 squared. And so this is just a simple derivative of the initial equation, which I personally find easier to use. The I in this equation obviously refers to intensity. The D refers to distance. Distance as in the distance between the X-ray source and whatever it is that you're concerned with. It may be the patient if you're talking about dose. It may be the image receptor if you're talking about exposure. And that's another point that I wanted to make right away, is that the inverse square law is often used in the case where I is equal to intensity, but the inverse square law is practical for other reasons as well. I can be equal to exposure. I can be equal to dose, and you can even use I as being equal to kerma. And so anytime you see a mathematical problem that refers to intensity, exposure, dose, or kerma, and the distance is changing, the inverse square law might be useful to you in solving that problem. And so let's look at a few sample problems. Problem number 1. A radiograph is made using a 72-inch SID, resulting in a receptor exposure of 0.01 milligray. What will the receptor exposure be if the SID is changed to 36 inches? So the thing to notice here is that the SID is changing. We have an initial receptor exposure of 0.01 milligray, and our initial SID is 72. Our new SID is 36 inches. So how will the receptor exposure change when we change the distance? A very important concept to think about. If our distance is decreasing, then our exposure, which in this case is represented as milligray, must increase. If our distance is decreasing, our exposure will increase. That's what the inverse square law tells us. So there's a few options that we can immediately eliminate. If our initial exposure was 0.01 milligray and we know our new exposure must increase, we can immediately eliminate A, and we can immediately eliminate D because we know our exposure, which is our milligray, must increase. Using the equation that we've already talked about, we start with our initial exposure, 0.01 milligray, and we multiply it by the squared ratio of the distances. And again, it's important to remember that this exposure is going to increase. The only way to do that is to insert our distance values like this, 72 squared over 36 squared, and that's going to equal 0.04. If we inverted these distances, the exposure would move in the wrong direction. So remember, the exposure needs to increase. We put our fraction in the right direction, and we know the answer is 0.04. A few mistakes that students make. Number 1, students will sometimes forget to square the distances. If you forget to square the distances, your answer will be wrong. Another thing to remember, mistake that sometimes students make, is they flip the numerator and the denominator. And again, if you do that, your answer will be incorrect. In fact, in this particular problem, the wrong answers that I included, A, C, and D, are all answers that you will get if you flip the numerator and the denominator or if you forget to square the distances. So let's look at another example. In this question, if an X-ray beam has an intensity of 1.2 milligray at 40 inches, what is the intensity of the X-ray beam at 60 inches? So again, remember the fundamental idea of the inverse square law. If our distance is increasing, then the milligrays must decrease. That is the inverse square law. So once again, there's a few potential options that we can immediately eliminate. Our initial exposure, our initial intensity, was 1.2 milligray. Our new milligray, our new intensity must decrease. So we can immediately eliminate 1.8 and we can immediately eliminate option C, which is 2.7. We simply start with our initial intensity of 1.2, multiply it by the ratio of the squared distances, which is 40 squared over 60 squared, and that's going to give us a new intensity of 0.53. And so we know the answer is D. And once again, if you had mistakenly forgot to square the distances, your answer would be wrong. If you had accidentally flipped the numerator and the denominator, in other words, putting 40 squared in the wrong place and 60 squared in the wrong place, you again would have got an incorrect answer. Here's another question. During a surgical procedure, the X-ray technologist stands at 1 meter from the C-arm for 1 hour and acquires an equivalent dose of 0.1 millisieverts. If the technologist had stood at a distance of 5 meters instead, what would their dose have been? So again, remember the fundamental ideas of the inverse square law. In this case, the technologist would be moving from 1 meter and hypothetically out to 5 meters. So our distance is increasing. And if our distance increases, then we know the dose, in this case, which is represented by millisieverts, must decrease. If the distance is increasing, the millisieverts or the dose must decrease. There's a few answers that we can immediately eliminate. A could not be correct, and D could not be correct because both of those are larger than the initial exposure. So we start with the initial exposure, the initial dose of 0.1, and again, we multiply it by a square of the distances, 1 squared over 5 squared, and that gives us a new dose of 0.004 millisieverts. And so we know the answer has to be C.